Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk about motion. In particular, we're going to talk about mechanics, which is the branch of physics that deals with the motion of bodies and the effects of forces on those bodies. We'll also mention two branches of mechanics. One of those is kinematics. Kinematics is concerned with the motion, but not necessarily with the forces that cause the motion or changes in motion. Dynamics, on the other hand, is a branch of mechanics that deals with the motion and the forces that affect that motion. You'll also hear the term translational motion. It's motion without rotation. It's straight line motion. Other important terms will be vector and scalar. A vector quantity or vector measurement is a quantity that has direction and magnitude or size. Oftentimes it's a measurement. The direction of that measurement is often indicated with a sign, either plus or minus. A plus sign indicates movement to the right, if we're talking about horizontal movement, or up, if we're talking about vertical movement. A negative sign, the opposite. A negative sign means to the left in the horizontal plane, or down in the vertical plane. Some examples of vector quantities are velocity, acceleration, displacement, and also force. A scalar, on the other hand, is a physical quantity or measurement that only deals with magnitude. Direction doesn't matter. It doesn't factor in to a scalar measurement. Some examples of scalars include distance, speed, mass, time, and electrical charge. Another term that we need to talk about is position. We will see it notated oftentimes as an X. It's the separation of an object from a fixed reference point. In physics, you have to set what's called your frame of reference. You have to set where your zero is. So the position is the separation from that 0 point. It's a vector measurement. So we'll indicate position with either a plus for to the right or up, or a negative for to the left or down. Distance, on the other hand, doesn't require a reference point. It's a scalar measurement. Distance is oftentimes symbolized as delta S. So let's say that a person travels north 10 meters, turns around on that same line, and travels back to the south 10 meters. So 10 meters north, 10 meters south. Well, they traveled a distance of 20 meters, 10 to the north and 10 to the south. That's distance. A term that oftentimes gets confused with that is displacement. Displacement is an object's change in position, and we'll oftentimes see it symbolized as delta X, change in position. Displacement is a vector, which means direction matters. So if we go back to this example and we ask for what's the displacement of this object, well, it started out right here. It went 10 meters to the north, turned around, came 10 meters back to the south. At the end of the problem, it's in the same place that it started. That means even though it traveled a distance of 20 meters, its displacement is 0. To calculate displacement, delta X, take your final position minus the initial position. When you want to find change in anything, this is the typical way to do it. Final minus initial. All right, next we want to talk about velocity. Velocity, or average velocity at least, is an object's displacement over time. So we might see it notated as V equals delta X over delta T. Again, remember, plus to the right or up, and negative means to the left or down. Now, velocity and speed are two terms that we need to make sure we know the difference between. Velocity is a vector, which means direction matters, whereas speed is a scalar. So for velocity, we might say that an object travels at 22 meters per second to the right, or plus 22 meters per second. Whereas speed, we would just say it travels at 22 meters per second. No plus, no minus, no right, no left, no up, down. Their magnitudes might be the same thing, Velocity takes into account the direction. Speed does not. So velocity and speed are not exactly the same thing. Velocity is a vector measurement or vector quantity. Speed is a scalar measurement or scalar quantity. We also need to look at what are called position time graphs. And we'll pull up one of those on the next slide. But in a position time graph, so this is position, x on the y-axis, time on the x-axis. Let's say we had a line that looked like this. So when we take the slope of a line, remember slope is delta y over delta x. So in this case, we would be dividing the position, the y variable, divided by the time. And remember that v equals delta x over delta t. This is average velocity, delta x over delta t. So when you have a position time graph, if you take the slope of the line, that slope is equal to what's called the average velocity. Now we'll come back to this term instantaneous velocity. During that time interval, or during any time interval, let's say we had a curve, we could calculate the average velocity by finding the slope between 2 points, maybe these 2 points. But because that line is curved, we know that that average velocity is not the exact velocity at every point in time. It's the average. The instantaneous velocity is the velocity at a certain instant in time. To calculate that, you're going to draw in what's called the tangent line. So let's say we wanted to know the exact speed at that point right there. We would come in and we would get a straight edge, and we would draw in a tangent to the curve. And then we would pick 2 points, any 2 points on this tangent line, and we would calculate the slope by doing delta y over delta x. That slope of the tangent line to the curve would give us the instantaneous velocity at this one particular point in time. So on a position time graph, slope is equal to the average velocity, and slope of the tangent line to a particular point is the instantaneous velocity of the object at that particular point. All right, so let's say we had a problem. It asked us to find the average velocity of the object shown in this graph between 0 and 3 seconds. So 0 to 3 seconds is right in here. We want to find the average velocity. So to find the average velocity, we're going to find the slope of that segment of the line. And to do that, remember, change in y over change in x. So at 3 seconds, our y coordinate is, we'll just say 30 meters. So we're going to take that y, 30. At 0, our y is 0. So 30 minus 0, change in y, over change in x. So the x coordinate that goes with the 30 is 3, and the x coordinate that goes with the 0 is also 0. So 30 minus 0 over 3 minus 0 is 30 over 3, which is 10. Our y axis is labeled in meters, our x-axis in seconds. So we're dividing 30 meters by 3 seconds. So this gives us a velocity of 10 meters per second, and it is positive, which means again either to the right or up. Now let's also say that we were asked to find the velocity at this point, or during this segment. So that's from 3 seconds to 6 seconds. We already know at 3 seconds our y coordinate is 30. So we're going to take that 30. At 6 seconds, our y coordinate is also 30. So 30 minus 30, change in y, over change in x, which is 3 minus 6. So 30 minus 30 is 0. When you have a horizontal line on a position time graph, that indicates 0 velocity. That means the object is stopped. It's not moving during this segment of the graph. Finally, let's say we wanted to know the average velocity between 6 seconds and 9 seconds. Hopefully, you can look at this graph and tell that it has a negative slope. It's sloping down and to the right. To calculate the slope of that line, again, we're going to find change in y over change in x. So at 6, our y coordinate is 30. So we're going to go 30. At 9, we're going to say our y coordinate is at negative 20. So 30 minus 20 over our 30 had an x coordinate of 6. Our negative 20, y coordinate of 9, so 6 minus 9. So we end up with 30 minus 20, so that's 50. And then 50 over 6 minus 9, which is minus 3. So we end up with negative 50 over 3. And again, that would be meters per second. Now, something that often confuses people is when we have not a line but a curve on a position time graph. We might say that this curve here is concave up. It's curving up and to the right. What this should tell you when you have a concave up curve like this, when we start over, what we can see is over here the slope is fairly low. But as we move toward the right, our curve is getting steeper and steeper and steeper. Remember, on a position time graph, slope represents average velocity. So over time, the slope is getting higher and higher and higher. That means with time, our velocity is increasing. Well, an increase in velocity over time is acceleration. We haven't mentioned acceleration yet, but acceleration is equal to a change in velocity over a change in time. So when you have a curve on a position time graph, that indicates acceleration. And in this case, through time, the velocity is getting higher and higher and higher. This means that this particular object is getting faster and faster and faster over time. All right, here's another example of a position time graph. In this graph, the slope is becoming less and less with time. You can see that it starts off being very, very steep. And what that should tell you that the object around point A, it's going really fast. Because remember, slope represents average velocity on a position time graph. But as we move across time, that slope is getting less and less and less and less and less. Since the slope is going down, the velocity is going down with time. This object is also accelerating. Acceleration doesn't necessarily mean speeding up. It means changing velocity. And in this case, that velocity is decreasing with time until we get to about this section when there's essentially no slope. And at that point, we can say that the object's pretty much stopped. So again, a curve on a position time graph indicates that the velocity is changing over time. It indicates that the object is accelerating. And remember that acceleration can mean that the object its velocity is changing over time. It can mean it's speeding up. It can also mean it's slowing down. Now here's some other examples of what curves on position time graphs might indicate. In the first one, we see that this one starts off with a negative velocity because the velocity is going down and to the right. But over time, that curve is curving up so that the slope is becoming less and less. So we might say that this object starts off with a negative velocity, but that its speed is changing in the positive direction. It has a positive acceleration. So over time, it's getting slower and slower. Whenever your velocity and acceleration have opposite signs, the object is slowing down. Whenever the velocity and acceleration have the same sign, the object is speeding up. So let's look at the second one. This one starts off with let's say a positive velocity because the line is sloping up and to the right. And over time, the slope of that line is getting higher and higher. So this one has a positive velocity and a positive acceleration. It's getting faster and faster with time. The third one, this one starts off with a negative velocity. And over time, that slope is becoming less and less. That means that it has a negative velocity and a positive acceleration. So in this part of the graph, it's slowing down. It slows down to essentially 0 right in here. It continues to accelerate, so now it's moving in a positive direction. It has a positive acceleration, which means in this section of the graph, it's getting faster and faster. Now if we look at this one, when we have a concave down slope, that means we have negative acceleration. So this one, this graph here starts off with a negative velocity because the line is sloping down and to the right. It's concave down, which means it also has a negative acceleration. Since the signs of those two objects those two quantities are the same, this one is speeding up. So over time, it's getting faster and faster. This one starts off with a positive velocity. It's sloping up and to the right. But the curve is concave down, which means the acceleration is negative. So since the sign of the velocity and the acceleration are opposites, that means this object is slowing down. In this section of the sixth graph, so in this section of this last graph, we start off with a positive velocity because the line is sloping up and to the right, but the curve is concave down, which means there's a negative acceleration. Again, the velocity and acceleration have opposite signs. So in this section of the graph, the object is slowing down. It slows down to about 0 right in here. Now it has a negative velocity because the line is sloping down and to the right. It also has a negative acceleration because the curve is concave down. These two have the same sign now, which means in this section of the graph, the object is getting faster and faster over time. So the moral of this story is when you have a concave up curve on a position time graph, that indicates a positive acceleration. When you have a concave down curve on a position time graph, that indicates a negative acceleration. We mentioned instantaneous velocity a minute ago. And that if you wanted to know the velocity at an exact instant, and you have a curve on a position time graph. So the red line on this graph is our curve. We want to know the exact speed at that point. Let's say the exact velocity at that point. So what we would do is draw in a tangent, like this green line, a line that touches that curve at only that one point. And then we would find the slope of that particular tangent line. So in this case, at 4, our y-coordinate, we're going to say is like, we're going to simplify there and just say let's say it's 4.5. All right, at 0, x equals 0, right in here, we'll say that our y-coordinate is 1.5. So to calculate slope, change in y. So we'll go 4.5 minus 1.5 over change in x, which will be 4 minus 0. So on top we get 3, on bottom we get 4. So our acceleration is 0.75. Here we're in meters. Here we're in seconds. We're dividing y by x, so 0.75 meters per second. So to find the instantaneous velocity from a position time graph, you draw a tangent line to the point of interest. You find the slope of the tangent line at that point. That will give you the exact speed at that moment in time. That's the instantaneous velocity. This graph is trying to show you that use that same concept. We have the black curve that's concave up. It starts off with a positive velocity because it's sloping up and to the right. Since it's concave up, it has a positive acceleration. Those two things have the same sign. That should tell you that this object is speeding up over time. It's getting faster and faster. And you can see it that if we wanted to know the instantaneous velocity at point A, we would draw in a tangent line. That line's not very steep. That tells you at point A this object isn't going all that fast. Well, let's say we want to know the exact velocity at point B, right in here. We draw in a tangent line. We find the slope of that tangent line. The velocity here is faster than it is here. The yellow line is steeper than the green line. Let's move on to point C. Again, draw in a tangent line. Find the slope of that line. Get an instantaneous velocity. This instantaneous velocity is greater than the instantaneous velocity at B, which is greater than the instantaneous velocity at A. So we're establishing, again, that if you have a curve on a position time graph that's concave up, it has a positive acceleration. And if the velocity was initially positive, those two things have the same sign, and therefore the object is getting faster and faster and faster across time. It's increasing in velocity. All right, we've already mentioned acceleration, but let's go back over it again. An acceleration is a change in velocity over time. We can notate it as A equals delta V, change in velocity, over delta T, change in time. Let's think about the units on that for a second. Let's say that we had a velocity of a change in, let's say we started off with a speed of 0 meters per second. And so we'll call that our initial velocity, V sub 0. Let's say 2 seconds later, let's say the velocity, which you might see notated as just V or VF, let's say the velocity is now 20 meters per second. And let's say that change occurred in a change in time of 2 seconds. So if we go back to this formula, plug in, acceleration equals change in velocity. Remember, that's final, which is 20, minus initial, which was 0, all over change in time. So 20 minus 0 over 2, we get 10. Now let's think about the units. The stuff on top was velocity stuff, so that's meters per second. The stuff on bottom, this was time, so that's seconds. So one completely correct way of writing acceleration is what you see here, 10 meters per second per second. And what this tells you is that every 1 second, the speed changes by 10 meters per second, or the acceleration changes by 10 meters per second. An equivalent way of writing that is meters per second squared. This unit and this unit are exactly the same thing. Remember what that meters per second squared means. It means each second the velocity is changing by that many meters per second. In this case, 10 meters per second. Some other reminders. We're talking about positive or negative. Let's don't use the word deceleration in this course. Let's talk about positive accelerations and negative accelerations. If an object has a positive velocity and a positive acceleration, the signs agree, the signs are the same. That means that this object is speeding up over time. Here, positive velocity, negative acceleration. The velocity and acceleration have opposite signs. That means this object is getting slower and slower across time. Here, negative velocity, negative acceleration. The negative velocity tells you that it's moving to the left or down. The negative acceleration tells you that it's getting faster as it's moving to the left or down. We know it's faster because these two signs agree. This one, the negative velocity tells you that it's moving to the left. The positive acceleration tells you it's accelerating in the opposite direction of motion. That tells you that it's slowing down. When the velocity and acceleration have opposite signs, the object is slowing down. We also want to talk about another type of motion graph, a velocity time graph. So in a velocity time graph, velocity is going to be graphed on the y-axis, time on the x. The slope of this curve, let's say we had a curve that looked like this. The slope of a velocity time graph tells you the average acceleration. So if we found the slope of this section of the line, we would find the average acceleration. If we wanted to know an acceleration at an instant in time, just like we did with a position time graph, we would draw a tangent line to the velocity time curve, find the slope of that tangent line, and that would give us the instantaneous acceleration at that point. Now, from a velocity time graph, you can also find the total displacement. And to do that, you're going to find the area under the curve. And we'll look at how to do that on a better graph here in just a second. In most cases in Physics 1, when we work problems dealing with acceleration, in most cases we're going to be dealing with what's called uniform or constant acceleration. We're assuming that the acceleration is the same for the length of the problem. Sometimes we call this uniformly accelerated motion. We have this group of equations in Physics 1 and in physics in general called the kinematic equations, which we will use pretty much every day throughout this course. Those equations only apply to uniform or constant acceleration conditions. And we're going to look at those formulas here in just a second. All right, so here's a velocity versus time graph. And let's say that we first wanted to know, let's say we want to know the acceleration of this object between time 0 and time 3 seconds. Remember that on a velocity time graph, average acceleration is equal to the slope of the line. So let's find the slope of this section of the graph. So at 3 seconds, our velocity is 16 meters per second. So we're going to say 16, y. We'll put the 3 as an x. Going to find the slope. So at 0, x equals 0, our y coordinate is 4. So we subtracted our y. 16 minus 4. We subtracted our x's on the bottom. 3 minus 0. We end up with 12 on top, 3 on bottom. So that's going to give us 4. Positive 4. Our units were the y units, meters per second, divided by the time units on the x, which were seconds. So we get positive 4 meters per second, or 4 meters per second squared. It's positive 4. This object started off with a positive velocity. It has a positive acceleration, which tells us from 0 to 3 seconds it's getting faster and faster. Now we look at this section of the graph. Let's say that we wanted to know the acceleration, the average acceleration between 3 seconds and 6 seconds. Well, we have a horizontal line. You guys know that the slope of a horizontal line is 0. So this object has 0 acceleration because the slope of a line on a velocity time graph is equal to average acceleration. Now in this section, that means the acceleration is equal to 0. That does not mean that this object isn't moving. This object is moving during this whole time interval right here at 16 meters per second. So it's moving forward. It's just not changing how it is moving between 3 and 6 seconds. Now let's look at the last section of the graph. In this section, we see that the graph has a negative slope because it's sloping down and to the right. Let's go ahead and calculate that slope. At t equals 6 seconds, our y is 16. So 16 and 6, y on top, x on the bottom. At 8 seconds, our y is 8. So 16 minus 8, change in y, over 6 minus 8, change in x. So that gives us 8 over minus 2, which equals negative 4. Negative 4 meters per second, or negative 4 meters per second squared. And remember, what that unit means is that each second, the speed of this object is changing by negative 4 meters per second. Another thing you'll oftentimes be asked to do from a velocity time graph is to find the displacement. To calculate the displacement of an object from a velocity time graph, you're going to find the area under the curve. So let's say that we wanted to know the displacement between 0 and 3 seconds. So what we would do is we would come to 0 to 3 seconds. We need to calculate this entire area underneath this curve. So this entire this area that I'm shading here. Now, notice that I shaded a triangle right here. We need to find the area of that curve. So with a triangle, to find the area of a curve, area is equal to 1/2 base times height for a triangle. So our base here is 3 units long, 0 to 3. And the height of our triangle is from 4 to 16, so that's 12. So 1/2 times 3 times 12, and that would be 18. So the area of this currently shaded part is 18. But it's the entire area under the curve. So we also need to find the area of this part. This part's a rectangle, and that rectangle is 3 long and 4 tall. For a rectangle, A equals B times H, base times height. So 3 long, 4 tall, the area of this part is also 12, or is 12. So the total shaded area here is 12 and 18, 30. Now 30 what? Let's think about the units. When we're finding area under the curve, we're essentially multiplying our y by our x. So we're multiplying meters per second by seconds. And when we do that, meters per second times seconds, we get meters, which is an appropriate unit for displacement. If we wanted to know the displacement between 3 and 6 seconds, we would find the area of this big tall rectangle. That rectangle is 3 wide, and it is 16 tall. So area of a rectangle, BH, 3 times 16, area of this part of the graph is 48 meters. We also could find the displacement between 6 and 8 seconds. And to find that displacement, we need to find the area underneath this curve. So we're going to again divide this into a triangle on top, a rectangle on bottom. So the triangle is from, let's clear it off so we can see our numbers a little bit better here. So our triangle is from 8 to 16, so it's 8 tall. It is 2 wide, so 1/2, 8 times 2. So that gives us 8. So the area of this shaded part is 8. Our triangle or our rectangle down here on the bottom is 2 wide, 8 tall, so base times height, 16. So our total area of all our shaded area here, 16 in the little rectangle, 8 in the triangle, 16 plus 8, 24 meters. It's positive 24 meters, which means even though this line is sloping down and to the right, during that time, the object is still moving in the positive direction. Has a negative acceleration. That's what the slope down and to the right means, but notice that the velocity, if we look over here on the y-axis, the velocity never gets below 8 meters per second during that section of the graph. So it's positive 8 meters per second. So it's still moving forward, but it's moving forward with a negative acceleration. So to summarize, if you have a velocity time graph and you want to find average acceleration, you calculate the slope of that particular line segment. If you want to know the instantaneous acceleration, you draw a tangent line to the point of interest, you calculate the slope of the tangent line, and that will give you the acceleration at that instant in time. If you want to find displacement, you find the area under the curve. These are the kinematic equations that you'll be using off and on all year long in this course. The top one shows us that Vx, sometimes you'll just see this written as V, that's final velocity, is equal to Vxo, which sometimes you'll just see written as Vo, that's the initial velocity, plus the acceleration times the time. The one underneath that X is the final position, is equal to x0, which is the initial position, plus Vxo, which is the initial velocity, times the time, plus 1/2 at squared. So in a lot of cases, you'll see this xo moved over to this side, subtracted from both sides, and instead of writing this equation in this form, you'll see it written as delta x. So it'll be final minus initial position is equal to VOT, initial velocity times time, plus 1/2 at squared. So that's just another way of writing this second formula. The final formula is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the quantity final position minus initial position. Very oftentimes, instead of writing it this way, you'll just see this written as delta x. So oftentimes you'll see v squared equals VO squared plus 2a delta x. Now remember that these equations only apply in cases of uniform or constant acceleration. One other formula that comes into play when you're working motion problems, if you have an object moving with a constant velocity, oftentimes the equation delta x equals Vt is very useful. So the displacement is equal to the velocity, which is constant, times the time. All right, another thing we want to talk about is the acceleration due to gravity. Acceleration due to gravity is notated with the lowercase letter g. And it's essentially how an object accelerates when it's falling. So oftentimes we'll talk about free fall. In this class, in most cases, when we're working with problems with free fall, we're going to be ignoring the effects of air resistance or drag. So we're going to pretend those don't exist, and we're going to assume that all the acceleration, at least the vertical acceleration, is due to gravity. The value of the acceleration due to gravity has been experimentally determined, and that value, you'll see a lot in this course, little g is equal to 9 point, sometimes you'll just see it written as 9.8, sometimes you'll see it written as 9.81 meters per second square. That means when an object is falling, every second its speed is changing by 9.81 meters per second squared. And that acceleration is always acting in the downward direction. That's why the negative is there. So the negative means acceleration in the downward direction. In English units, you might see this written as negative 32 feet per second squared. It's a special case. Free fall is a special case of uniform acceleration. And we'll see lots of problems in this course that deal with uniform acceleration and free fall. Here are a couple of graphs related to free fall. This first graph is a graph of, let's say, velocity. It says speed, but let's call this a velocity graph against time. Now remember, on a velocity time graph, the slope of the object is equal to the average. Again, remember, on a velocity time graph, the slope of the line is equal to the average acceleration. So we can see that this object is accelerating, and that the acceleration is essentially constant because the slope of this line pretty much stays the same. Now here we have a position versus time graph. So this is an x against t graph. Notice that this graph is curved and that slope is increasing over time. Remember, on a position time graph, if you have a curve, that means there's acceleration. These graphs are both graphing the same thing. They're graphing an object in free fall. Now realize that our motion detectors, or at least our photo gates, can't tell negative and positive. So this thing has a positive slope. This thing is concave up. When in reality, the acceleration should be negative 9.8. And that's just due to the fact that our computer doesn't know the difference between up and down. But again, velocity time graph, slope is equal to acceleration. If this were free fall, the slope of this particular part of the line should be about negative 9.81 meters per second squared. On a position time graph, a curve indicates acceleration. This particular object is accelerating because it is freely falling. All right, in this particular picture, we can see what happens when an object is dropped. So at the very top, the object starts off at time 0 with a velocity of 0. It's dropped from rest, from 0. After 1 second, its velocity is about 9.8 meters per second. And to be exact, we're going to say that's negative 9.8 meters per second because it's acting in the downward direction. Between 1 second and 2 seconds, the thing accelerates due to gravity, which, remember, it accelerates about 9.8 meters per second every second in the downward direction. So after 2 seconds, the speed is 9.8 plus 9.8 more, which is 19.6, negative 19.6 meters per second. After 3 seconds, the velocity increases by another 9.8 meters per second. So it becomes negative 29.4 meters per second. Every second, in this case, the velocity is changing by negative 9.8 meters per second. All right, the final thing we want to talk about in this screencast are what are called motion or particle diagrams. So here we take an object and we think of it as if it's just one particular point, usually one particular point at its center of mass or center of gravity. And the motion diagrams show us a series of images of an object moving, and it records the object's position between every recording of the object's position. The time between those recordings is the same. So it's showing us the position after equal amounts of time. So let's look at what a diagram like this might look like. So here are 6 different motion diagrams. So let's right now just concentrate on the top one. So the particle starts out at time 0, right there. After, let's say, 2 seconds, after 1 second, equal time intervals. Let's say the time between all these little dots, all these little black balls, is 1 second. So after 1 second, this object has now moved from 0 to 2 meters. So it changed its position, a change in position of 2 meters in 1 second. So that essentially tells you that from 0 to 2 seconds, it moved 2 meters in 1 second, 2 meters per second. From 2 meters to 4 meters, that change happened in 1 second as well. So it moved 2 more meters in 1 more second. From 4 meters to 6 meters, that change happened in 1 second. So again, 2 meters per second. So what we could say about diagram A is that this object is moving forward because it's moving to the right. Every time interval, it moves the same displacement. So we could say that it's moving to the right with a positive constant velocity. Now let's move down to motion diagram B. All right, so notice this one, time 0 here. Time 1 second, it's moved to 1 meter. 2 seconds, it's moved to 2 meters. 3 seconds, it's moved to 3 meters. 4 seconds, 4 meters. So every second, this object is moving 1 meter. This object is moving with a velocity of 1 meter per second. It's moving with a constant velocity of 1 meter per second. So we could say that the object A is moving about twice as fast as object B, but both are moving forward with a constant velocity. Now let's move down and look at C. So notice at first, the first 2 dots are very close together. That means in 1 second, This little ball barely moved. This little object barely moved. Between the second ball and the third ball, that distance is a little bit further. So it moved a little further in that second. The third ball to the fourth ball, it moves even further. The second ball to the fourth ball to the fifth ball, it moves even further. And the fifth ball to the sixth ball, it moves even further. So what we're saying is that after every second, it's moving faster after every second. It's going further every second. So this object is moving forward. It's getting faster every second. So we're going to say this object is moving forward and accelerating. It has a positive velocity and a positive acceleration. Every second it's getting faster. So going down to object D, or motion diagram D. Between the first black dot, the first particle, and the second particle, the object moves 3 meters in that 1 second. Between the second and the third, it moves 3 more meters in 1 more second. And between the third and the fourth, it moves 3 more meters. So this object is moving forward. It's moving forward with a positive velocity, a positive constant velocity of 3 meters for each second, 3 meters per second. Looking down to E. In the first second, this object moves from a position of 0 all the way over to a position of 4. In the second second, it moves from a position of 4 to 6. So it doesn't go as far during that second second as it did in the first second. From the third dot to the fourth dot, it goes even a less amount of distance, and that continues to happen. So we could say that this object is moving forward because its position is increasing, but because the amount of displacement decreases between each time interval, it has a positive velocity but a negative acceleration. This object is moving forward but slowing down. Maybe it's a car with the brakes on. It's moving forward, but it has a negative acceleration. Finally, let's look at the last one. From the first particle to the second particle, it goes a very far distance, from 1 to 6. From the second particle to the third one, it doesn't go as far. From the third to the fourth, it goes even a less amount of distance. So this one too has a positive velocity, but a negative acceleration. Again, it's like, think of it like a car that's still moving forward, but the brakes are on. Positive velocity, negative acceleration. Hope that helps.